Hello everybody, and welcome back to my SB2 channel. This lecture is all about precipitation reactions. We're going to start by introduction. We're going to be looking at the solubility guideline for ionic compounds. I have a little bit on the exchange reactions as well as the ionic equations and spectators, and we also have a practice at the end. Now, just a heads up, this lecture is a little bit longer than what we typically have. So I want to ask you to bear with me pretty tightly and enjoy the ride, right, for the next few minutes together. Okay, so starting by our introduction, a precipitation reaction is a type of chemical reaction where we have two aqueous solutions react to form an insoluble solid, which is known as precipitate, right? And that is going to stay solid and kind of separates from the solution. Now, keep that in mind anytime that we say aqueous solution, we are referring to a solution that has water as the solvent. Now, here's an example. I have barium chloride reacting with sodium sulfate. On my product side, I have barium sulfate, which is going to stay as a solid, so that's my precipitate. But your sodium chloride is going to remain as a dissolved species in our solution. Now, think about how we got this precipitation, right? Your barium sulfate. So, barium is your cation, which is positively charged. Sulfate is your anion, and that is negatively charged. So you've got a pair of oppositely charged ions in our aqueous solutions that are kind of attracting each other so strongly so that they can actually overcome the forces keeping them away, right, dissolved in our solution. And that's exactly how we got the formation of this precipitate. Okay, now we're going to be looking at the solubility guideline for our ionic compounds, and I'm going to start by kind of definition of solubility. So here it says the solubility refers to the amount of a substance that I can dissolve in any given solvent, right, at a specific temperature. So that means if I change my solvent, right, or if I change my temperature, I'm going to have different solubility. Okay, think about the solubility as like dissociation of your solute, right, in order to form a homogeneous solution. Now, unfortunately, there is no straightforward rules based on solely, let's say, physical properties such as ionic charges, right, that can help us to predict whether a particular compound will be soluble or not. However, we have our, experimental observation that has been done and measured by our scientists, and they have developed general guidelines to predict the solubility of an ionic compounds in water. Okay, and I'm going to show you on the next slide. Okay, so here is our solubility guideline table. So starting by acetate, this would be always soluble. Nitrate is always soluble as well. For the halides, such as chloride, bromide, and iodide, they're going to be always soluble unless we have them with these cations, which is silver, mercury, and lead. Then we have sulfate, which is typically soluble, unless we have that with the strontium, barium, mercury, or lead. Then we have carbonate. This one is typically insoluble, unless we have that with compounds like ammonium, right? Alkali metals, which is going to be the, group 1 metals such as sodium, potassium, okay? Hydroxide would be typically insoluble unless we have that with ammonium and again the alkali metals, calcium, barium, and strontium. Phosphate would be typically insoluble unless we have that with these cations, ammonium and alkali metals. And we also have sulfide, right? That is typically insoluble unless we have that with these cations, which is ammonium, the alkali metals, calcium, barium, and strontium. And again, you don't need to really memorize this table. This would be provided to you, right? Okay, so here is pretty much a summary on how we can predict whether a precipitation is going to form when we are mixing our strong electrolytes or not. Okay, so there are going to be a few steps here. The first step is identifying the ions in our reactants. So our job is to break down the strong electrolytes into their, cations and anions, and keep that in mind. You would only do that for your strong electrolyte. Then we need to consider the possible cation-anion combinations, right? So our job is to combine the cation from one reactant with the anion from the other one to form the potential product. And the next step is checking our, solubility with the table that you saw in the previous slide, right? So that we can decide if something is going to stay as a precipitation or we need to have that as a dissolved product, okay? And I'm going to show you an example on the next page. So follow me on the next page. So here's an example. It says, will a precipitate form when we have a solution of magnesium nitrate and sodium hydroxide? So we're mixing these two, okay? So to determine if we have a precipitate or not, I need to look at my 3 steps, right? So let's take a look at step number 1, which is identifying the ions for our reactants. So my magnesium nitrate is going to fully dissolve into magnesium and nitrate because I know all of my nitrate are going to be soluble, right? This is what I got from the table. I also know that if I have hydroxide with sodium, right, which is group 1 cation, they're going to be also fully soluble into their ions. So I have sodium and hydroxide. Now I need to look at the possible cation-anion combinations. So I'm going to have my magnesium from magnesium nitrate, and I'm going to potentially combine that with my hydroxide from sodium hydroxide. So that could be one potential product, which is magnesium hydroxide. I'm going to grab my sodium, right, my cation from sodium hydroxide, and combine that with the nitrate from magnesium nitrate to form sodium nitrate. Okay, so I got these two potential products. Now, the next step is checking the solubility, right, with my table. So according to my table, magnesium hydroxide is going to be insoluble. So that is going to be my precipitation, right? But sodium nitrate is going to stay soluble in water, right? So that will remain dissolved. So let's just put all of these together. Here is my balanced equation for my precipitation reaction. I've got magnesium nitrate reacting with sodium hydroxide, and they both are soluble, and they are producing magnesium hydroxide, which is my precipitation. And I always have my sodium nitrate dissolved, right, in water. Okay, cool, cool. Okay, now the next kind of reaction that we're going to be looking at that is what is known as exchange metathesis reactions. So these are the reaction in which the cations and the anions are going to exchange their partner, right? And that's why we call them the exchange reaction. And if you look at what I have here, kind of generic reaction, we have AX reacting with BY, and we are producing AY plus BX, right? So the precipitation reactions that we just talked about it, as well as many of our neutralization reactions are going to follow this pattern. That's a very common pattern in chemistry. So for example, if you have silver nitrate reacting with potassium chloride, they're going to produce silver chloride and potassium nitrate, right? And that is a very good example of exchange reaction. Okay, so now how we can actually balance these kind of reactions, there are going to be a few steps, okay? So that would be very similar to what we had for our precipitation reaction. We need to identify the ions in our reactants, right? So you can use the chemical formulas for each of your reactant to determine which cation and anions are going to be presented. Then we need to predict the products. So we're going to combine the cation from one reactant with the anion of another, right, in order to form our products. And then you're going to use your ionic charges, right, to determine the correct subscript in your chemical formulas. Then we need to check the solubility, right? We need to verify the solubility of our product using the solubility rules in our table. For a precipitation reaction, right, specifically, we need to have at least one product that must be insoluble in water. And then at the end, I need to balance out my equations. So I want to make sure that I'm following the law of conservation of masses, so everything has to be balanced. Okay, so let's consider the precipitation reaction between these two compounds. I'm going to start by writing my molecular equation, by which I mean I'm going to show all of my reactants and products as it is without breaking them into ions. Okay, so that will be lead nitrate reacting with your potassium iodide, and I'm going to have lead iodide and potassium nitrate. So when you have everything included without breaking them into their ions, we call that molecular equations. Then I'm going to go by complete net ionic equation. So in my ionic equation, I need to represent all of my soluble strong electrolytes as dissociated ions. Okay, but if you have anything that is solid, you would leave that as solid, right? Even if you have something like a weak electrolyte or non-electrolyte, we're not going to touch them at all. Okay, so in this example, my lead nitrate is a fully soluble compound. Again, how do I know that? This is from the table, right? So nitrate are going to be always soluble. I also have potassium iodide, which is also fully soluble. So anything that is fully soluble, you're going to break them down into their cations and anions, right? On the product side, I have lead iodide, which is a solid, so I'm just going to write that as it is. And then I have potassium nitrate, which is also a fully soluble compound, so I need to break them down into their cation and anion, okay? Now, the next step is focusing on only the species that are involving in our reaction. That means we need to exclude all of our spectators' ions. So what are the spectators? Those are the ones that you see them on the reactant side and the product side the exact same way. They're just there to balance out the charge, but they're not doing anything other than that. So for example, here I have my nitrate. I can cross them out. I have my potassium, which is another spectator. So you can remove all of your spectators. Whatever is left over is presenting your net ionic equation. So the actual ionic interaction between these two cation and anion is the reason that we are forming this precipitation, right? So let's summarize what we did. We start by writing the balanced molecular equation for the reaction, and then rewriting the equation to show the dissociation of the soluble strong electrolytes into their cations and anions, right? And then we identify the spectators and we cancel them to focus on the species involved in the actual reaction, okay? Cool, cool. So I'm going to show you a practice on the next page. Okay, so here's our practice. It says write the net ionic equation for the precipitation reaction that occurs when we have aqueous solution of calcium chloride and sodium carbonate. Okay, so I'm going to start by writing the balanced molecular equation. I know that my calcium chloride is going to be CaCl2, and my sodium carbonate is going to be Na2CO3. I also know that both of these are soluble, right, based on my table. So I'm going to write them as AQ, okay? Now, the next step is predicting the product, right? So I'm going to grab my calcium from the first compound and then combine that with my carbonate from the second one. And we also have sodium chloride. According to the table, calcium carbonate is a solid, but sodium chloride is going to stay dissolved. Then I need to rewrite the full ionic equation by showing all of my soluble strong electrolytes that are dissociated into their ions. So I need to start by calcium chloride, right? That's the first one. You can separate them into calcium and chloride. Then we have sodium carbonate, right? I'm just going to write my calcium carbonate because that is a solid, right? We also have sodium chloride that I need to dissociate them into sodium and chloride. The next step is identifying your spectator ions, right? That are going to be appear on both sides of our equation and then cancel them. So here are my spectators. I have sodium and chloride. So I'm going to cross out my chloride as well as my sodium. Then I can write the net ionic equation, which is going to be the reaction between calcium and carbonate, right? That is how we can get calcium carbonate, which is our precipitate. Excellent. Thank you so much for bearing with me. I know this one was a little bit longer than usual. Thanks for watching. And let me know if you have any questions, any comments. I would love to hear from you guys. Don't forget to, hit the subscribe button so you're not going to miss out our future videos. Thank you, and take care. I'll see you on the next one very soon. Bye-bye for now.